Hi all, I want to welcome you to today's lecture section. Today will still be a continuation of our module 4. The last time in the last lecture we talked about how to draw the 2D and the 3D structures of molecules. Today will be an application of that knowledge. But before we start, as usual, I have a wonderful quote here. It says, the quote is by Michael Jordan, a Hall of Famer basketball player, one of the greatest in the game of basketball. So he said, I've failed over and over and over again, and that is why I succeed. What this is telling us is that no matter how much time you fail, you always go back and fix the reason why you failed and keep pushing forward. And that is a very good message. I like the quote very much. Let's take it off from there. Today our learning objectives are simple. We're going to be using the electronegativity to predict the polarity of molecules. That's the first thing we'll look at today. We use electronegativity to predict the polarity of molecules. And then we also use electronegativity with the combination of what we talked about last time, the VSEPR model. Remember, VSEPR means the valence shell electron pair repulsion model, to predict the polarity of covalent bonds. Let's get it started. First of all, remember, when we talked about two types of covalent bond, we said there are two types of covalent bond, the polar covalent bond and the non-polar covalent bond. And in a polar covalent bond, we said that, of course, the two types of covalent bonds involve the sharing of electrons. But in this case, the sharing of electrons are not equal in, so it's unequal in polar covalent bond, whereas in non-polar covalent bonds, the sharing of the sharing of electrons are equal, to say. So in a non-polar covalent bond, the sharing of electrons are equal. That electron pair, the bonding pair of electrons that is shared between two atoms involved, are actually equal. And in fact, this type of bonding is also called pure or ordinary covalent bond. So any non-polar molecule will have this kind of bond. Now, another important thing we need to know is electronegativity. Electronegativity is defined as the tendency of an atom to attract shared pair of electrons to itself. Now, the ability of an atom to attract a shared pair of electrons. And interestingly, electronegativity increases when you go from left to the right of the periodic table. In fact, remember earlier we talked about that elements that are towards the right of the periodic table, the non-metals, have the ability to accept electrons. So that makes sense. As you go even right of the periodic table, as you go towards that direction of the periodic table, electronegativity increases, and as you go down the group, it decreases. So we're going to see the table of electronegativity and try to put these things together. So electrons of covalent bonds are attracted towards atoms with the highest electronegativity. Atoms that have high electronegativity will always get the share of these electrons more in a covalent bond. And because they get it more, that type of bonding tends to be highly polarized and will result to a polar covalent bond. So what is bond polarization? A bond polarization is a product of that unequal sharing. It's a product of unequal sharing. So it results when shared electrons are being attracted to a more electronegative atom of the bonded pair of electrons. So if you have two atoms here, let's say atom A is bonding with atom B, and one atom, let's say atom B, has more power to attract more electron cloud to itself and leaves only small for atom A, what it simply means is that most of those electrons will be found at any point in time towards the B atom. And in fact, what happens is that it makes the B to assume what we call a partial negative, and A will have a partial positive. But we're going to see this as we move on in this lecture. So the electronegativity table as given to us by Mr. Pauling helps us to understand this polarity of bond. You see, this table is an arbitrary table as developed by Pauling, It increases, like I said earlier, as you go across the group from left to the right, it increases towards this way and decreases as you go down the, and it makes sense because elements to the right of the periodic table are non-metals and they have the ability to accept electrons and attract more electrons to themselves, and that is why they actually have higher, and in fact the most electronegative element is fluorine itself. Fluorine is the most electronegative element in the periodic table. And what do you find out here? The group 8 elements are not actually represented because these guys do not go into bonding and they do not attract or release any electrons to themselves. So that is why if you look at this place, you don't find them reported in the periodic table. So we're going to be applying this table as we move on. Now, bond polarity is actually classified based on the polarity of a covalent bond. So what actually happens here is that the difference, the absolute values in the electronegativity difference, the change in between two bonded atoms. So assuming we have two atoms, let's say X and Y, and we find the electronegativity difference between these two. We find a change in the electronegativity. If that change in electronegativity is between these three values, now let's look at those three values and what it means. Now, if the value of their electronegativity is less than 0.5, that type of bond is nonpolar, despite the fact that it may have a little bit of polarization, but it's classified as a nonpolar bond. And this usually takes place between two nonmetals and either two nonmetals or a nonmetal and a metalloid. Again, when the difference in electronegativity is larger, between 0.5 to 1.9, the bond that results in that type of arrangement is a polar covalent bond. And again, this can happen between two nonmetals or a nonmetal and a metalloid. Then when it is greater than, when it's very high, the difference between these two are very high. In fact, actually, this usually results when you have an element towards the extreme right combining with an element towards the extreme left, which is the metals, which are the metals. When they combine together, the electronegativity difference is usually too high, and this kind of case is a type of ionic bond. Now, the kind of bonding they form here is not a partial bond. It's not a partial. The type of polarization is not a partial polarization, but this is usually a full polarization. And remember, we have talked about that ionic bonds are formed when one atom loses electron and which is being accepted by another atom. Of course, like I said, this happens between a metal and a non-metal. Now, although the best way to recognize at times the electronegativity table and the difference could be a little bit misleading. The best way to identify a metal and a non-metal is just to note that there will always be a metal combining with a non-metal in that compound. That gives you, this is an ionic compound, ionic. Once you see a metal inside that compound, it is ionic. At times, don't base your judgment in this case on what the difference in electronegativity might be. Now, let's solve some problem. Now, let's see, this is interesting. Now, bond polarity more on bond polarity. For atoms that are bonded by a covalent bond, the more electronegative atoms, like I said, will assume a partial negative sign. And the ones that is less electronegative will assume a partial negative sign. If you see example here, if you look at hydrogen and chlorine, if you go back to that table, let's see it. Hydrogen has an electronegativity of 2.1. Chlorine has an electronegativity. Let's look at chlorine. At this point, has of 3.0. So if we go back there and look at the electronegativity difference, let's see, change in electronegativity. So what is going to be is an absolute value. So you can do anyone, it doesn't matter. So I'm going to say 3 minus 2.1. That difference should give me, okay, let me confirm that number again. Yeah, that's it. So that should give me about 0.9. Now, with this kind of classification, this bond is a polar covalent bond. And what happens? The bond becomes polarized. Now, chlorine, like I said, chlorine has 3 as its electronegativity value. Hydrogen has 2.1. Because this is more electronegative, it assumes what? It assumes a partial negative sign, represented by delta minus. Whereas the hydrogen assumes a partial positive sign, which is represented by a delta positive sign. And if you actually look at what the orbital image looks like orbital diagram. Now, this is a molecule of chlorine, a molecule of hydrogen chloride gas. Now, there's a bond. Like I said, I've showed you the bond here. This is the bond here. Now, between these two, look at the relative share of electrons. Chlorine is getting more share in this relationship than hydrogen. And that is the reason why this bond is actually a polarized bond. And the direction of polarization is written from the positive side to the negative side. That is how the direction is written. And in fact, it's usually one single arrow that has the positive sign at the tail as a cross. So that is how you write or show your dipole. We call this the dipole moment. The dipole moment, or the bond polarization pole. So whichever one you call it, that is going to work. So we're going to see this as we move on. Now, the first example we're going to be seeing, it says, using the electronegativity table, classify the bonds as non-polar covalent, ionic, polar covalent, and indicate the polarity using delta notation, and show the direction of the covalent bond. Now, what are we going to do? We're going to be using look at it. The question says, using the electronegativity table. So, now the first question is between chlorine and fluorine. We're going to go there. Now, if we go to the table, again, we see chlorine is 3.0. We saw it earlier. Fluorine is 4.0. So I'm going to go back to the question. Now, in your exams, you'll not be expected to memorize this. This is going to be provided for you. So now, for me to calculate the change in electronegativity, the change in En, now I can do it. It's an absolute value. So if you get a negative, make it a positive. So it doesn't matter. So chlorine, I can start from anyone. So what I have here is my chlorine, and I say chlorine is 3.0 and fluorine is 4.0. So the change is going to be 3.0 minus 4.0. And of course, this is going to be an absolute value. If you do 3 minus 4, it's going to give you -1, but an absolute value is going to give you what? 1. Now, it gives you 1. What that tells you is that if you look at that classification of this bond, when it is between 0.5 to 1, this is a polar covalent bond. So we go back there. This is a polar covalent bond. The bond will have to be polarized. So I'm going to redraw this bond. I'm going to draw Cl connected to F. Because this bond is a polarized bond, what it means is that fluorine is more electronegative. It's going to assume a partial negative sign. The less electronegative will assume a partial positive sign. And then since the direction is going from positive to negative, the dipole moment will be drawn from positive towards this way. And of course, because of the classification, I already said that this is a polar covalent bond. We get to the next one. Now, silicon and hydrogen. Again, you go back to that table. I will always advise you to have this table handy with you. Silicon there. Silicon, if you look at it very well, silicon is 1.8. And again, hydrogen is 2.1. So if I check the change in their En, it will give me 1.8 minus 2.1. Of course, this is an absolute value. So if you do it, it's going to give you 0.3. Now, if you look at that, let's look at the classification. When it is it is less than 0.5. That means this bond will likely be a non-polar covalent bond. Now, despite the fact that it is a little bit polarized, let's look at it. So you're going to draw it this way. Si will be going to H, and of course, this is actually polarized because this is between these two. Which one is more? You see, hydrogen is actually more what? Electronegative. So it's going to take the negative sign. This is going to take the positive sign. Now, this actually has a little polarization to it, but because it is this polarization is not enough to make it a polar covalent bond. Therefore, this is going to be a non-polar covalent bond. It's a non-polar covalent bond because of that classification. The next one, nitrogen to a hydrogen. Again, let's see. Nitrogen, if you look at it, I know hydrogen is 2.1 now. I've used it a couple. So what is nitrogen? Nitrogen is 3.0, just like chlorine. So I go back there. So this is, you can write it anywhere. So I'm going to just write my 3.0 here for this one and 2.1. If I change the change in En, the difference in En is going to be 3, of course, an absolute value minus 1. And this, of course, is going to give us 3 minus 1 is going to give you 0.9. Again, this value is above 0.5. And of course, that will tell you is in the region of polar covalent bond. So what do? I'm going to redraw this. I'm going to draw it. My nitrogen will be connected to my hydrogen. Of course, nitrogen is more electronegative, so it's going to have the negative sign. This is going to be a positive sign. And of course, if you look at this one now, the polarization goes from positive to negative. So I'm going to draw my arrow will be facing this way from this, and this is a positive sign. Of course, this is what? A polar covalent bond. That is how you solve those problems. Let's go to problem 2. Still the same thing. Basically, the same thing that we're doing. In this case, now I have a metal and non-metal. Like I told you, if you see a metal and non-metal, just know that this is an ionic bond. But we still have to do that ritual. Let's try to see. Now, sodium, if you look at it, sodium is a metal. If you look at the electronegativity table again, it's 0.9. So it's actually 0.9. And fluorine is 4.0. Fluorine is 4.0. We visit the couple. So the change in En is going to give us 4.0 minus 0.9. And when you do your subtraction, of course, this is an absolute value. It's going to give you 3.1. That's very high. So if it's very high, let's look at that again. Of course, if you look at this value, when it is above 1.9, this is purely an ionic compound. Like I told you, you can notice that by seeing a metal first in this compound. Having a metal that tells you it's ionic. So I'm going to draw this like this. Now, it's connected to F. In this type of bond, it is usually not a partial positive because it is ionic. So how do you put it? Usually this forms a full negative bond. This forms a full positive bond. And of course, the direction of polarization will still be from positive to a negative. That is what you do in that problem. Now we go to BR and O. Bromine, again, I'm not going to look it up again. If you have your electronegativity table, you can always pause this problem. Use your electronegativity table. Pause this video rather. Use your electronegativity table, solve the problems, and then come back and check for your answers and proper comprehension. So this is 2.8 for bromine. Oxygen is 3.5. If you look at the change in En, that will actually give you 3.5 minus 2.8. And if you check the difference is going to give you 0.7. Of course, it's an absolute value. And then, if you look at it, it's above 0.5. This tells you that this bond is polar again because it's greater than 0.5. So if I'm going to redraw that, we're going to redraw it PR. We go to O. Oxygen is more electronegative. This is less. It gets a positive sign. So the direction of polarization will be this way. And of course, this is what? A polar covalent bond. The last, but not the least, fluorine to oxygen. Let's look at what that gives us. From fluorine to oxygen, again, fluorine is 4.0, oxygen is 3.5. If we look at the change in En, it's going to be 4.0 minus 3.5, and that will give us actually 0.5. Now, if you look at that again, it is 0.5 and greater. This is going to be a polar covalent bond. So we go back there and we draw it. So our F to O, this is more electronegative. It gets this. This is less, and then the bond polarization will be from this way to this way. It's going to give you, and of course, this is what? A polar covalent bond. That is how you solve these problems. Like I said, always feel free to pause this video and come back. Now, what we've just done so far is looking at the polarity of a bond. Just two atoms that are sharing two electrons, a pair of electrons. But this is not always the case in molecules. Some molecules actually, like hydrogen chloride gas or hydrochloric acid, will have just one bond between them. And because it just contains two atoms. What if when we have molecules that contains more than two atoms, how can we figure out their polarity? And that is what we're going to be doing next. So a polar molecule will always be a molecule that contains a polarized bond, of course, a bond whereby there are two atoms whose bond they are sharing is polar. And secondly, that charge is distributed non-symmetrical. Non-symmetrical means is that the dipole moments are not cancelling out. What does that mean? Okay, let me give you a good example. If I have a molecule, let's say A is connected to X and connected to A again from both sides. If you look at this now, this molecule seems to be symmetrical because it has the same, when we talk about symmetry, in this case, has to be with when you have the same atom attached to a central atom. What it means is that if this bond is polar, it has a dipole going this way and has another dipole going this way. The strength of these dipoles are equal. One is going towards the positive, one is going towards the negative. What it means, a positive and negative equal magnitude is going to give you 0. So the resultant at the end of the day will result to a bond that is not, a molecule that is not polar, despite the fact that there is a possibility of having a polar bond within it. Now, so, and what about a non-polar molecule? A non-polar molecule, like I said, will contain no polarized bonds at all. Either you have a molecule without any polar bond, or a molecule that can contain a polarized bond, but the bonds are distributed symmetrically, or they cancel out, like what I just did here. If the bonds cancel out, it remains non-polar. But if the bonds don't cancel out, it remains polar. And like I said, this is the continuation of the last class in this module. If you want to figure out if a molecule is polar, what do? You need to first of all figure out the 2D Lewis structure. Then from there, you're going to know the name of the electron geometry, which is the 2D name. You figure out the molecular geometry, which is the 3-dimensional structure. And then it is the 3-dimensional structure that tells you whether it is polar or not. Because the 3-dimensional structure or the molecular structure will give you the information if the dipole moment present in that molecule will cancel out or not. And we're going to see some example. Now, I have a chart here that will guide you to do this. You see, this chart will help you to do eliminations by the time you want to figure out polarity of molecules. You're not going to have this in exam, but this is just for you to study. Let's see what it looks like. You see, here I have a molecule. Most diatomic molecules that have the same thing connected to them, of course, they will have no bond polarization. I didn't have that example, but it's a very good thing to see here. So, example, let's say hydrogen. Hydrogen is connected to a hydrogen. Hydrogen has electronegativity of 2.1, has 2.1. If you calculate the EN difference, the EN difference is going to give you 2.1 minus 2.1. And this is going to give you 0. Remember, from 0 to less than 0.5 will be what? Anything less than 0.5 is going to be nonpolar. So this molecule is nonpolar. In the first place, it does not even contain a polarized bond. Now, when a molecule has 2 atoms, we did this example in one of the ones we did, hydrogen and chlorine. You see, chlorine is more electronegative than this by far. This is about 3.0, this is about 2.10. So the difference is 0.9. This bond is a polar bond. So whenever you have a diatomic molecule that contains 2 different atoms, whose difference in electronegativity is greater than 0.5, that is actually a polar molecule. Now, the example I gave you in the previous page, when I tried to draw this, look, this is what it is. If you have a linear molecule, this is the central atom now, that has two same atoms attached to it. This makes it symmetrical. This molecule is symmetrical and therefore non-polar. The same thing happens when you have a central atom that have 3 same attachment. Look at this. Attached to the central atom. This molecule is symmetric and therefore is non-polar. However, if you have 3 atoms attached, but you find out that this and this are the same, so the polarization will cancel. But if you look at this one, too, it's not going to cancel. So what it means is that this atom is also polar in this direction. So this will be a polar. It is non-symmetric around this central atom, and therefore it's going to be a polar molecule. Again, when you have atoms that contain lone pairs, a good example here is water molecule that contains 2 lone pairs. Now, if there is no lone pair on this molecule, water molecule would have been looking linear. But this molecule is actually a bent shape, like we did with the VSEPR model. This bent shape makes it non-symmetric, and if this non-symmetric molecule contains a polarized bond, it's going to be a polar covalent bond. Again, if a molecule contains 4 of the same atoms attached to the central atom, it remains non-symmetric, just like we have in this case of this one and the case of this. So this carbon tetrachloride is non-symmetric because It contains carbon here is attached to four of the same type of atoms. The atom again is symmetric and is nonpolar. And lastly, if you have 3 different things attached to an atom, here remember there are 3 different things but they are the same. Here they are the same. But the difference is that this structure is actually a trigonal pyramid. Trigonal pyramid. And the reason why it's a pyramid is because it has a lone pair, making it non-symmetric and therefore a polar covalent molecule. So we're going to try to apply this in the next few examples. Let's start from the first simple one. It says SeO3, selenium trioxide, is dash molecule that contains dash bonds. What do we do first? Let's try to draw the Lewis structure. I'm not going to put you through the process of drawing the Lewis structure. I'm just going to draw it what it looks like. The direct molecular geometry. If you draw a complete Lewis structure of this molecule, it's going to give you this. And if you analyze this using VSEPR model, this gives you a trigonal planar because it has no lone pair at all. So the final shape of this molecule is a trigonal planar. However, silicon has 3 of the same attachment attached to it. Like I tell students, do not even bother. Just look at, if you can memorize this table, if it has the type of attachment, it is non-polar, it is symmetric. This molecule is symmetric. Despite the fact that if you check the electronegativity difference between selenium, let's see it, selenium and oxygen, remember oxygen is 3.5 in electronegativity, and this is what? Let's go to selenium. I have my table here. If you go to selenium, selenium is 2.4, so we go back. Selenium is 2.4. So if you do the difference between selenium and this, if you look at the difference now, so this is going to give you 5 minus this is going to give you about 1.1 in electronegativity difference. The En difference is going to give you about 1.1. So the change in En is actually going to give you about 1.1, which actually supposed to make this a polar molecule. Yes, there is a dipole moment from this point to this point. There's a dipole moment from this point to this point. There's a dipole moment from this point again to this point. Remember, this is the cross here. This is the cross. Now, there are 3 dipole moments in this molecule, but unfortunately, because this molecule is symmetrical, it is highly symmetrical, it is non-polar in overall. The overall molecule, it's non-polar because of the symmetricity of this molecule. So we can now say that selenium is what? Is a non-polar molecule. It is a non-polar molecule that contains a polar bond. So number 3 will be that contains polar bond. It contains 3 polar bonds, but because it's symmetric, it is not a polar molecule. So that is what is there. Now let's now take it off from there. In problem, so it said determine the polarity of the following molecules and show the direction of bond polarization or dipole. So what are we going to do? The first thing you need to do is to draw the Lewis structure. I'm not going to show you how to do that. I've done a couple of these Lewis structures in the last lecture. In module 4, the last lecture I did, I showed you a couple of these examples on how to draw it. I'm going to tell you what the overall geometry is. So the geometry of this molecule, if you draw it well, it's going to give you, according to the VSEPR model, it's going to give you something like this. So I'm going to use my normal red. I like writing with red. So it's going to give you H connected to carbon. Carbon has 3 bonds connected to this and a lone pair. So this is actually the 2D. So remember, in VSEPR model, we don't actually consider this double. So in VSEPR model, what we look at is the overall structure will just be H is connected to C is connected to N. Now remember, the lone pairs at the central atom doesn't matter. Our interest is just this. So this is how this molecule looks like. Now, when you look at this molecule now, remember, if you check the En difference between carbon and hydrogen here, now remember, carbon is 2.5, hydrogen is 2.1. Now, nitrogen is about 3.0. Yeah, nitrogen is 3.0. We can always go back here to check those. Nitrogen is 3.0, hydrogen is 2.1, and then we're correct. And carbon is about 2.5. Yes, so I was correct in all of them. You don't need to memorize those. Now, if you check the EN difference between these two, from 2.5 minus 2.1 is going to give you about 0.4. What it means is that this bond is actually very nonpolar. This is a nonpolar covalent bond, although it has a little bit of polarization. But the difference between this one and this one, 3.0 minus this gives you 5. That means this bond is polar. So in this direction, carbon to nitrogen is polar. This is a little bit polarized, but because it falls between this, so our interest wouldn't go here. So if I'm going to draw my bond polarization, I'm going to be drawing it from, okay, if I'm going to take this off, yeah, I'll definitely do that to have enough space. So I'm going to take this off. Remember, now my direction of bond polarization will be from this direction. Okay, yeah, I'm going to draw it up. From here, remember this is from positive to negative in this direction. And remember again, this is more electronegative again. Again, this guy, because this molecule is linear, like what we have in that table. If you look at that table again, we are having something that looks like this. 3 different atoms in a linear molecule like this. It is non-symmetric and it's going to be a polar molecule. So this is going to be a polar molecule. And in fact, this will be, if you look at this now, this will be, carbon is less electronegative, is going to be partial positive. This is more, is going to be partial negative. The direction of bond polarization is going to look this way. The second one, NCl3, if we draw it. So now, if you draw the normal structure of this, it's going to look this way. It's actually a trigonal pyramid. It has a lone pair here, so we're going to have hydrogen here. If I'm going to draw it, it doesn't matter the way you draw it. So if I'm going to draw it the way it looks like, actually, in the rating, this is, if I'm going to have a bond that is going away from me, I'm going to have hydrogen here. I'm going to have one that is coming close to me. And then I'm going to have another one that I can see to the right in my plane. And then it has a lone pair here, of course. It does have a lone pair. Remember, a lone pair is one pushes the thing down. So this is a lone pair here. Now, so this is a trigonal pyramid. If you look at this now, the difference between these two is that nitrogen is about 3.0, this is about 2.1. So these bonds, individual bonds, are all polar. So hydrogen is 2.1, nitrogen is 3.0. So what it means is that this bond is polar. So if you do the difference, 3.0 minus 2.1 is going to give you about 0.9. So the En is going to give you about 0.9. So this, it has 3 polar bonds. Now, but remember, the shape is not a trigonal pyramid whereby it is connected and cancelled. The presence of this lone pair makes it non-symmetric. And therefore, remember, this is usually less electronegative. And then this is more electronegative, assumes a negative sign. So if you're going to draw, this looks like a pyramid. If you're going to draw the direction of polarization, I found that it is going from the positive side of this place to up. And this is the direction. So at the end of the day, this molecule is what? Is a polar molecule. It is polar. Remember, this one is also a polar molecule. We go to the next question. Now, it says determine, of course, the same question again, the polarity of the following molecules and show their direction. Again, if I draw the overall structure of sulfur trifluoride, what are we going to see? We're going to get something like this. So you're going to get, okay, I'm going to use my red as usual. You're going to get this, F, and then there are 2 lone pairs that are seated here. Those 2 lone pairs are what makes it non-symmetric and pushes these bonds down. Again, if you consider sulfur and fluoride, fluoride, of course, is the most electronegative element. So fluorine is going to have negative. This is going to have a positive. This is going to have negative. This is going to have a negative. So there are, you look at it now. If this molecule, if there was no lone pairs on top of this atom, this molecule would have been a linear molecule. And the bond dipoles would have cancelled out. But if you look at it, it is bent. And the direction of polarization is going to be from this side that is positive, which is the top here, going down this way. So this will be the direction of polarization. And therefore, since this molecule is non-symmetric, molecule is polar, it is non-symmetric because of the lone pair. The lone pairs it contains. That's what makes it polar covalent bond. Again, we go to the next one. We go to this molecule. If you draw the structure of this molecule again will look this way. You don't need to show the lone pairs anyway. I said in this type of, you don't need the lone pairs when you're drawing the 3D structure, so I'm not going to show the lone pair. If you look at the structure of this molecule now, this is a trigonal pyramid. This is overall a trigonal pyramid. And then this is the central atom. Now, if you look at oxygen is the second most electronegative, so it's 3.5. Carbon is 2.5. So at the end of the day, carbon is 2.5. Oxygen is 3.5. So if you look at the difference, it's highly polar. So this is going to be partial positive. It's going to be partial negative. And if you look at carbon and bromine again, what would that give you? Let's see what carbon and bromine is. Bromine is, if you look at bromine is 2.8. Okay, you see that? Bromine is about 2.8. So what that tells you is that bromine is 2.8. If you look at the difference between carbon and bromine, is about 0.3. So that this bond is not even polarized at all. So the polarity resides in this side of the bond. Resides in this part of the bond. So what does that mean? It is going from a positive sign here up to a negative sign. So this is the direction of polarization. Again, this is a polar covalent compound. Again, it is not symmetrical because you don't have the same atom attached on all sides of this central atom, carbon. We move to the next problem. It says, determine the polarity of the following molecules and show the direction of bond polarization. Again, we look at it. This is nitrogen molecule. Remember what I told you? Every molecule, of course, nitrogen usually have 3 bonds in East Lewis structure. But in this case, we want to see, it doesn't matter. You don't have to consider it. This is how a nitrogen looks like. So nitrogen, we know, individually, nitrogen atom has a very high what? Distance. So it's 3.0. So this is 3.0. This is 3.0. If you do the difference, 3.0 minus 3.0 is going to give you 0. So there's no bond polarization in this molecule because it's symmetrical. So this molecule is non-polar. And the reason why it is non-polar is because the change in En is equal to 0, or you can say it is symmetrical. It has 2 atoms on both sides. And again, we look at SiO2. Let's try to draw this. If you draw the structure of SiO2, it looks like carbon dioxide. SiO2 will look this way. I'm going to draw the actual Lewis structure, then I can tell you what it looks like. If you draw the actual Lewis structure, it's going to look like this. So remember, in VSEPR model, we don't have to show the double bond. So I'm just going to say O and O. And there's no lone pair there. If you look at this molecule, if you look at the difference between oxygen, of course, is 3.5. And silicon, let's look at the electronegativity of silicon. Silicon is about 1.8. Okay. Silicon is 1.8. Now, silicon is about 1.8. If you look at the difference between silicon and this bond is a polar bond. Significantly, a polar bond, about 0.7 difference in En. The change in En is about 0.7. So it is reasonably polar. But something is happening here. What do you think? No, it's greater than, what am I saying? It's greater than 1.8 actually. So it is 3.5 minus 1.8. If you put that in your calculator, at times I don't want you to try to do this in your head. Just put that in your calculator so that you don't make mistake. This gives you about 1.7. That is a lot. So you see the difference between this, the electronegativity between this is about, the change in En here is 3.5 minus 1.8, and that gives you about 1.7. Very high polar bond. But what is happening? There is no lone pair. If there was a lone pair here, this molecule would have been a bent molecule, but there's no lone pair. What it means is that there is a polar bond going to this way, there is another dipole going to this way. But because the same atom is attached on both sides of this molecule, these dipoles are going to cancel out each other. Therefore, this molecule is a non-polar molecule. So, sulfur dioxide is a non-polar molecule. And the reason why it's the non-polar molecule because it contains a polar covalent bond, contains two polar bonds, but, or you can say that cancel out. It doesn't say that cancel out. Cancel out. And hence, make it non-polar. Or you can say, if you don't want to say cancel out, you can say it is, the molecule is symmetrical. And molecules that are symmetrical will remain non-polar. So silicon dioxide, despite the fact that it has two polar bonds, is a non-polar molecule. The last, but not the least, this is the last page we're going to be doing in this case. Again, if I draw the structure of this guy, I'm going to have something like this. I'm going to use my red for now. I'm going to have C connected to Cl, and then this will be connected to, if I have this, hydrogen, I'm going to have another one, H here, and I'm going to have another one. Now, again, remember, every carbon-hydrogen bond is a non-polar bond. You can memorize that. Most organic compounds like your gasoline, your kerosene, your kerosene, your methane, and all the rest of them are carbon and hydrogen chains. That's what they contain. So they are highly non-polar. So because the difference between these two guys is about 0.4. So this is a highly, is a non-polar bond, highly non-polar bond. So I'm not even going to concentrate on attention there, but I'm going to check carbon and chlorine. Again, you remember chlorine is 3.0. Now chlorine is 3.0 and white carbon is 2.5. So if you look at the change in En, this is going to give you 3.0 minus this will give you 0.5. It is in the polar covalent bond range. We know these ones are not polar. What it means is that this is less electronegative, it's going to be a plus. This is more, it's going to be partial negative. And what it means is that the direction of bond polarization is going to be from this carbon here towards this guy. So, therefore, this molecule is a polar molecule. It's a polar molecule, and it is not symmetric. Not symmetric. And why is it not symmetric? It doesn't have the same thing connected all around it. That is why it is not symmetric. The last we're going to be studying is water molecule. Of course, most of you know water as a universal solvent. The shape of water is a bent molecule. It looks this way. Oh, no, I'm not going to draw it. I don't draw it with my red. Water is a bent molecule, so if I'm going to draw my oxygen this way, draw my hydrogen, draw my hydrogen. And of course, it has two lone pairs on the side that push these bonds down according to the VSEPR model. So if I'm going to put my lone pair and show you how it looks like, these are the two lone pairs that's pushing it down, making this non-symmetric. Again, remember, oxygen has an En of 3.5, hydrogen 2.1. So the difference in them is actually very, very high. The difference in this is actually very, very high. So if you check it, it's going to give you about 1.4. That is actually a strong difference in electronegativity. Now, however, this molecule is not a linear molecule. The shape of this molecule is bent. And bent molecules are non-symmetric. And because non-symmetric and has a polar covalent bond, therefore, it is a polar molecule. Water is, in fact, of course, water is known to be one of the most polar liquids we know that dissolves both polar substances and ionic substances as well. So the direction of bond polarization is going to be from, I have a space here, from positive, because this is partial positive, this is partial negative. It's going to be from this side towards this side. So this is the direction of bond polarization or you can say the dipole moment. So far we've been able to see how you can use the VSEPR model to decide the polarity of a molecule, and also use electronegativity to decide the polarity of molecules that just contain only 2 atoms, the atomic molecules. Once again, I'm going to put a stop at this point. If you want to talk to me about the class, if there are things that are not clear, always feel free to come to my office, or you can reach me through the usual channels. Thank you again for listening, and have a wonderful time. Bye.